have acid-base reaction, you have oxidation reduction reaction. So we call it redox reaction. Redox means reduction oxidation reaction. And then we discussed about the working with solution. If you are given a solution, you need to prepare a new solution with a new concentration, how you can do. And then we discussed briefly about the quantitative analysis, because this topic will be something you do in the practical training chemistry, in the practical chemistry course. Basically, it will have this course in the second semester of the first year. So we move to the first topic, evidence of a chemical reaction. So by definition, a chemical reaction is a process, a phenomena, where one chemical compound is consumed and one new chemical compound is generated. So if you observe the color change, that means the absorption of the solution is changed. In other words, the interaction of the solution with the light you send to the solution will be changed. That indicates a new chemical compounds appear or generated in this solution. So it means when you have a color change, you can say there is very likely a chemical reaction happen. When you observe the formation of gas, so let's say when you put two chemicals in a solution, and then you see the evolution of gas, like the picture you see here, that means you start from the solution liquid, in the liquid phase, and then you observe something produced in the gas phase. So definitively, the compound in the gas phase should be different compared with the liquid phase compound that you put inside. So that means a new chemical compound is generated. So in that case, you can say there is a chemical reaction happen. The third case, when you observe the formation of a solid or precipitate. So let's say when you put the liquid together, and then you observe the appearance of a solid compound. So that means solid compound should be different compared with the liquid. Excuse me, can you mute your microphone? Phan Tuấn Tú, can you mute your microphone?
Cái mà là cái lói bột này mới được như thế này mới lên xô chứ lúc cho.
Phan Tuấn Tú, can you mute your microphone? Tú. Phan Tuấn Tú, can you mute your microphone? Yeah, probably you turn on the section and then you left. It's not very nice.
You could kick him.
Okay, so when you have a solid compound appear, that means the solid is totally different, at least in the phase, compared with the reaction you put inside. In that case, you can conclude a new chemical compound is appear. So that means the chemical reaction happen. When you see the emission or absorption of heat, that means the reaction happen, because when it's emits heat, that means the process is exothermic, and when it absorbs heat, cool down the environment. So that means the process is endothermic. So it indicates a chemical process. But be careful, because not all the time. Let's say when you have a phase transformation from the solid to liquid, very likely the process will be also endothermic. So you see when you melt the solid compound, the temperature in the environment will be decreased. So you see the absorption of heat, but that would not chemical action. That's a physical transformation, physical process. That's a phase transformation. So when you, to conclude, when you see the emission or absorption of heat, it could be a correction, but it can be also a physical process. So be careful with that. How about the emission of light? The emission of light mean the emission of photon, and photon carry energy. So that means when you see the absorption of photon, that means the process really energy in terms of radiation emission, in terms of in the form of photon. But be careful, not all the time this process with the emission of light can be linked with a chemical process. It can be only the physical process. For example, here you see, if you take cadmium selenium, this CDSE, and you put in the suspension, in the solution, you illuminate with photon, and then you turn off the photon, turn off the light. Then you see the emission. And depending on the size of this particle, you will see different emission, that means different color. And this process is simply due to the fact that CDSE is a semiconductor. So basically, when you classify the matter in terms of electrical conductivity, you will have conductor. For example, metal like copper, gold. You have a semiconductor like cadmium sulfide. You have isolator. For example, plastic. Okay. So semiconductor, that means it's conduct, but with a low conductivity. And the reason that you have semiconductor with a low conductivity is because you have a band gap. So you have the ground state, we call the valence band, and the excited state, we call conduction band. Valence band, that means where you see the accumulation of valence electron. So when the electron excited to the conduction band, it's become conducting. So that's why they call the conduction band. So now the electron is located here in the valence band because they are valence electron. So when you excite the photon with the photon, then the electron will excite here in the conduction band. If then you turn off the photon, this electron will be back to the valence band, and because at the excited state, that means at the conduction band, the energy is higher than the valence band position. So when it be back from the conduction band to the valence band, then it will release photon with the different energy equal to what we call the energy gap. Equal, this is energy gap. Okay, so with different value of the gap, the energy of photon emits will be different. So it's explained why when you change the size of CDSE, it will change the emission. So you will see the different color here from the blue color to red color, because you modulate, you tune the band gap. And then you see that the process is simply, you give the same CDSE particle, it's only the absorption and emission process. So this is not a chemical reaction at all. That is a physical process. So you see, when you see the emission of light, it can be a chemical process, but it can be simply physical process. Okay?
Cái loại điện thoại cho từng người được, hay là bảo những người có bệnh bị bệnh sĩ là phải mua iPhone không phải như thế. Sĩ cũng là một nhu cầu đi nhá. Rồi, chúng ta sẽ đến với câu hỏi tiếp theo của bạn Lai Công nghệ. Bạn hỏi là theo anh Dương Dê thì giữa màn hình IPS 2K supramolet full HD1.
Thank you. Thank you for giving the chance to having this kind of lecture. Okay, you see the job of lecture is not very simple job, right? Sometimes it's quite stressful with this kind of event happen. Okay, then we move to the aqueous solution and solubility. First, what could be a solution? A solution is a homogeneous mixture of two or more substances. Yeah, you need at least two substances. Then in the solution, you have two components. One we call solute. That is the component that is dissolved. And you have a solvent, which is the component that does the dissolving. So in a solution, the solvent is usually the substance present in the greatest quantity. So you have a two component, one solute and one solvent. So we have higher quantity in terms of volume, in terms of number of mole, then which is called solvent. The component which has lower quantity, we call solute. An aqueous solution is a solution in which the solvent is water. So let's we consider the case, the test is coming. So basically, it will take this solution, water, right? Ethanol in water. So in this homogeneous mixture, in this solution, which one is solvent and which one is solute? So for the alcohol you drink, basically the maximum percentage of ethanol is about 42% of ethanol. So it means ethanol is solute, and water with more than 50% will be solvent. But when you work in the research lab in the chemistry, sometimes you can take a solution with 20% of water in ethanol. So in this case, the water becomes solute and ethanol become solvent. Okay? So it's really depending the quantity of component which will decide which one is solute and which one is solvent. Okay? Not all the time water is solvent, but in aqueous solution, for sure, water is solvent. Now, when you have a solution, we look at the electrolytic property. That means the property to represent the conductivity, electrical conductivity of the solvent. The electrolyte is a substance whose aqueous solution contains iron. So the electrolyte solution conduct electricity. So imagine that you have three solution difference. You put here, which is non-iron compound. We call the molecular compound. And the second solution, you have a few iron can be generated when you put in the water. And the other solvent, or other solution, sorry, where you have many iron generated. Then you make the connection with a light like this one. So you see that for the case of no iron, there is no conductivity. So you can see that the lamp is not lighting. And then when in the case you have many iron, the conductivity is excellent. So the lamp light strongly. The case of non-electrolyte solution, when it's substance that does not form iron in the solution. So for example, if you take the fructose sugar, you dissolve in the water, so the molecule will remain So in that case, you will have no ion solution, and this will be not conducting. So you will not see the electricity can circulate in this situation. So when you have an ionic compound like sodium chloride, you put in water, an ionic compound when dissolved, the ions are solvated, for example, surrounded by water molecule and unable to recombine. So for example, if you take the sodium chloride, you put in water, so you will see that the sodium and chloride will be separated, and surround this sodium, you should present like sodium like this. And then you have molecule water, molecule water, molecule water, molecule water. So that is solvated sodium. So what could be the consequence of this one? So basically, the solvated sodium and solvated chloride cannot be recombined anymore to make the crystal. If you want to take again the sodium chloride crystal, you need to remove the water, so to reach the saturation solution. Then the precipitation, the crystallization start to happen. The second result of this dissolution is that basically, you know, the size of the sodium ion. You consider like a sodium ion itself like a spherical particle, then it has a diameter. But then when you put in water, the solvated ion, the solvated sodium get much bigger. What could be the consequence? It makes that the mobility of sodium solvated could be much slower compared with the sodium non-solvated. And also, when is, if you, for example, if you take a host material with the distance d nanometer like this, and then if you put sodium ion itself without any solvated configuration, then it can get in and get out easily. But if you have a solvated sodium, this solvated sodium ion will get in. So that means insertion into this host slowly with much more difficulty. Also, the escape of this solvated sodium also very difficult. And in some circumstances, when you have solvated sodium get inside the host, the spacing d can be extended. Okay, so it changes the property of the host, which have several consequences. Another result of this solvated process, let's say, if you want to, you have given that you have two ion like this one. Now, if you want to eliminate it, you want to do the filtration to remove the sodium plus and chloride minus by using a membrane. So you take the solution on top of this one, and you do the filtration. So you take, let's say, all of sodium and chloride up, and only water will be down. So you have drinkable water. This this process make from the source solution, salted water, to become drinkable water is extremely important in the context of Vietnam now, because you see that in the Mekong Delta, you have the sea level increase. So the salted water penetrate inside the Mekong Delta, So the water in the depth inside the delta become not drinkable because the high concentration of salts. So if you want to make this water become drinkable water, you need to remove sodium chloride. So one possibility is using the membrane. So now in terms of the concept, you can imagine that when you have a membrane, that means you have some hole, some pore, right? Such could make the water molecule go through, but that should keep the sodium not penetrate through that. That means that you need to make the size of the pore quite small to let the sodium retain on top of that. Now, if you consider only the sodium without solvated environment, then the size of the pore should be very small. But luckily, because you have solvated, so the size of sodium become larger, so you can have the membrane with a larger size. So the efficiency, that means the number of the amount of water can be go through that is much faster. The amount of water can be increased. So you have the performance of the filtration process increased thanks to the solvatation process of sodium and chloride ion. Okay. And here again, you need to distinguish the energy you need to dissolve sodium chloride or salts in general in water, which is different compared with the lactic energy. That means the energy you need to break the crystal of sodium chloride solid into the sodium and chloride gas. Here you have a sodium solvated and chloride solvated, not gas phase. Okay, so the two energy are totally different. The lactic energy is extremely high, but the energy you need to do the dissolution is quite small. So you see that if we put sodium chloride in water, it dissolves quickly. If you have molecular compound, that means the compound is not ionic, which not contain the ionic bond, but only the covalent bond. Then when it's dissolved in water, it's been dissolved in the whole molecule form without forming ion. Okay, so let's say if you take a methanol, Ca3, always all the bond inside is covalent bond, you know, in the previous lecture. So when you put in water, you can make the solution of Ca3OH water, but then the molecule will be fully retained without the forming of any ion. So now we talk about the strong and weak electrolyte. So strong electrolyte, by definition, is almost 100% of the compound dissolved in the solution as ion. Example, all the water solute ionic compound like sodium chloride, calcium chloride, and so on. Strong acids and strong base. Strong acids, for example, is 2SO4. Strong base like sodium hydroxide. They will dissolve almost fully in water. So in that case, you have strong electrolyte. You have a weak electrolyte. That means the compound, only one part of that will be ionized in the solution. Most exist mostly at the molecular form. For example, if you take a weak acid, acetic acid, you will see when you put in water, you will have, or in other solvent, it will have equilibrium between the molecular form and, so you have molecular form and the ion form. Okay, so you will see it as When you put in the solution, this compound exists both in the ionic, in the ion form, and in the molecular form. So in this case, we call the weak electrolyte. Later, for now, in the general chemistry one, you accept this definition. Later, when you learn in the second semester, general chemistry 2, for you, it's become much more simple. You also consider the strong electrolyte is dissolved in the solution and having this equilibrium. So both the strong electrolyte and weak electrolyte have equilibrium, and they have the equilibrium constant. Equal to S plus Cl minus over HCl. So the same here is become CH3 COO minus S plus and over CH3 COOS molecular. So in the case of strong electrolyte, this value is very high. For example, you can reach 10 power 4, 10 power 7 if you want. But for the case of weak electrolyte, this value of equilibrium is small. For example, if you have the equilibrium equal to 1, 1, that means 10 power 0. So you see that depending when you are given an molecule, an electrolyte, to define whether it's strong electrolyte or not, you don't need to look at the solvent, you don't need to look at the nature of the chemical bond inside the compound, but you ask for the equilibrium values. If you have a high equilibrium constant value, then you can say it's a strong electrolyte. If you have small equilibrium constant value, you say that it will be a weak electrolyte. Because later you can imagine the term aqueous here, that can be different solvent. This can be, for example, acetone nitride, it can be DMF, whatever. So when you change, if you are given a same compound like acetic acid, but you change from water to another solvent, for example, acetone nitride or DMF, this value of equilibrium constant will be changed. So if you are given the formic acetic acid, and then you are asked whether it's a strong electrolyte or not, it's quite difficult to say. You need to understand also the interaction of this compound with the solvent, because we have a solvatation process. That means the interaction of the solute and the solvent molecule. And that's interaction, that solvatation will decide the equilibrium constant. And when you have an equilibrium constant value, you will know, we will have an idea about the strong or weak electrolyte. Okay, so now for the general chemistry one, we have not discussed yet about the equilibrium constant, equilibrium chemistry. So the definition is quite relative, quite descriptive. So, but later in the general chemistry 2, with the concept of chemical equilibrium, so when you know the equilibrium constant, it must be easier to own the quantification. Okay. So now, if you are given 3 compound, sodium chloride, sodium hydroxide, carboxylic acid, carbonic acid, and methanol, and then you are asked to put the 3 compound in the 3 picture. You can say that for that will be here CH3OS, because when it dissolves in water, it will not generate any ion, so there is no conductivity. In the case of weak electrolyte, you can put a 2CO3 here, because it will have equilibrium, H plus HCO3 minus, and also HCO3 minus in equilibrium with H plus CO3 2 minus. So you see, because they exist two equilibrium, so they exist both in ion and also in the molecule. So the conductivity of this compound will be low. For the case of sodium hydroxide, so it will fully making sodium plus OH minus. So you see that it will generate a huge amount of solvated ion, so the conductivity increase. So now, if we need to discuss about solubility, the solubility is ability to dissolve in water. Of course, we can talk about the solubility in other solvent as well. But if you don't mention about the solvent, we should understand that when we talk about the solubility, that means the solubility in water. If they talk about the solubility, anyone talk about solubility in any specific solvent, they need to mention about the solvent. Otherwise, we should understand people are talking about the solubility in water. So if a compound is readily dissolved in water, it means it's soluble. If it's not soluble in water, we call insoluble. Okay? So you have here different solubility rules for ionic compound. The first rules you can see in the table. The statement says that the group 1A and ammonium compound are soluble. So there's no exception. On the source of the group 1A compound, including lithium, potassium, sodium, and also ammonium, are soluble. In water, we are talking about. And the second solubility rule says that the acetates or nitrates are soluble. There is no exception. The third one says that most chlorides, bromides, and iodide are soluble. You have some exceptions which are not soluble. For example, silver chlorides, silver bromides, and less iodide. The compounds are not soluble in water. Most sulfates are soluble. You have some exception. For example, barium sulfate is not soluble. Silver sulfate is not soluble. Carbonate, most of carbonate are soluble, are insoluble. Most of soluble, except for example, group 1A carbonate, sodium carbonate is soluble. Lithium carbonate is soluble. Potassium carbonate is soluble. You have some exception. Is soluble. Most are insoluble. Some exception. You have some exception. Group 1A hydroxide is soluble. Calcium hydroxide is soluble. Chromium hydroxide is soluble. And barium hydroxide is soluble. So basically, if you want to work well and easily with the solution chemistry, then you need to have the idea about the solubility rule. I put one emphasis here. That's something very important and interesting. This one, phosphate. We say that most of phosphates are insoluble. Most of phosphates are insoluble, except the group 1A phosphates and ammonium phosphates. So you know that to make the fertilizer NPK, okay? So B representing for phosphorus. Okay, so the component they use to generate phosphorus in NPK fertilizer for the agriculture ammonium ammonium, that means Na4 SBO. Okay, so you see that's the difference between this one and ammonium phosphate is one hydrogen still remain in this one. So you have only two diazonium replace two hydrogen. So in that case, you have diammonium phosphate. And you can see this compound very soluble in water. So this compound is also soluble, highly soluble in water. Compound is produced by very simple reaction between Na3 plus H3BO4. Okay, and then this H3BO4 is made by the reaction of H2SO4 plus B2O5, and the B2O5 is come from the mineral we call apatite. Okay, so in the apatite you have B2O5 plus several metal. The metal here can be aluminum, can be magnesium, can be also cadmium. So what could be the problem? The problem is that in the DAB company, they take the apatite mineral, making the reaction with sulfuric acid, generating phosphoric acid, and then make the reaction between the phosphoric acid with ammonium, with ammonia, sorry, Na3 to make DAB. And then they observe what they observe when they sell the DAB to the customer. They say that your DAB is not good enough because when the customer, when the farmer apply the DAB in water, it's not fully soluble. What is something strange? Because the DAB, you know, that is highly soluble in water. So what could be the issue? Why the DAB from the company in Lào Cai, when they put in water, is not fully dissolved. It remains some solid, and the farmer do not like this kind of phenomenon. They think that the DAB has low quality. Even the rice and other plants develop very well with the DAB Lào Cai. So one possibility is that this DAB contains the impurity, which is MbO4, which is phosphate source of M here, which M could be ammonium, magnesium, and cadmium. And you see that most phosphates are insoluble. So if you have sodium, if you have aluminum phosphate, if you have magnesium phosphate or cadmium phosphate, it's not soluble. So when you put DAB with the impurity, which is ammonium phosphate, you apply in water, the DAB soluble, but the ammonium phosphate remain, and the farmer observe the remain solids insoluble, which is the ammonium phosphate, and think that the DAB have low quality. So now one of the research and development question of this DAB Lào Cai company, they are request help from the chemist, and they require that they will need how to say, very active research development contribution from the chemists in Vietnam now is how to make DAB with less impurity of metal phosphate with ammonium phosphate or magnesium That means make DIB more with a higher purity, with less impurity, to make it faster soluble in water. You get what I mean? So you see that you learn this solubility is something not very important. You can do, you can calculate the amount of the salts soluble in water easily. That you learn in a high school if you want. Even at the secondary school, you start to learn about it. And as high school, for preparing the national exam in the grade 12, you know very well this one process. But then maybe, probably, you don't know, this simple question remain in a huge value, economic value, in a big company like DAB. DAB is one of 3 big companies produce NBK and produce DAB for the whole country, for the whole Vietnam. And because of the low solubility of the DAB in Lào Cai, thus make the farmer in Vietnam prefer DAB from China. And they need to pay 2,000 more expensive per kg of DAB for the Chinese product. Even the quality will be the same, but only the fact that the DAB of Lào Cai, when you apply in water, still remains some solid parts. And because remain the solid parts, the farmer don't like this, and they prefer paying higher price, 2,000 per kg is a huge amount for the farmer, for the Chinese product. You see, so the simple solubility question can be an object for your career, research development career in the future if you want. You see, okay? Any question on this?
Nope.
No? All good?
Yes.
Actually, you see, you may know that the production technology they use nowadays in DAB Lào Cai, in Lào Cai province, for production of the DAB is imported technology from Europe. So when the European company develop this technology, they use the apparatus with a high quantity. That means very low content, no impurity content of the metal like ammonium, mesoneum, and so on. But then when they apply this technology in Vietnam, because the quality of the apparatus is lower, so they got a problem with the solubility. So basically, in China, they should have some technology to improve the quality of the apparatus before putting in the production technology, or during the production chain, they would have something to eliminate aluminum phosphate, mesoneum phosphate, and so on. So it's something DAB Lào Cai request the chemist, Vietnamese chemist to have. Okay, so solubility and electrolyte concept. Solute substance are either electrolyte or non-electrolyte. Most soluble ionic substance are strong electrolyte, because when you put the ionic substance inside, it will get solvated. So you have an ion. So when you have an ion, solvated ion, you have strong conductivity, or you have a strong electrolyte. Solid molecular substance are non-electrolyte or weak electrolyte, because you have the solvatation equilibrium. Okay, and few molecular substance such as hydrogen chloride are strong electrolyte, because these compounds are highly polar. So when you put in the water, the solvatation increase, the interaction with water increase. So you shift the equilibrium forward, so the equilibrium constant is high. Now, we talk about the classification of the chemical reaction. In general, to make the put the chemical reaction in 2 big classifications. We have acid-base reaction, and you have redox reaction. That means reduction oxidation reaction. So what could be the difference between acid-base reaction and the redox reaction? So if you take the case of a very representative reaction of acid-base, you have Na3 S plus Na3, you have NS4 plus. In the previous lecture, when you look at the geometry of this compound, you see that Na3, you have this geometry, and you have a pair of electrons here. So here you have a pair of non-bonding electrons, and the S plus, if you consider, compare with the stable electron configuration, the stable electron configuration will have 2 electrons. This will be not an octet because the hydrogen you have only 2 electrons. Then how to reach S plus to reach this configuration with 2 electrons? So you can imagine that S plus make the bonding here. So you have now the sharing electron. So the hydrogen will have 2 electrons, and then the NS3 now have 4 covalent bonds. Okay. So here you can say that you can imagine like you can understand the acid-base reaction like the 2 electron is delocalized to the S plus to make the covalent bond, and we can say this one is delocalization of electron. Okay, so now the non-bonding electron in the Na3 is shared between the nitrogen and hydrogen in the form of proton. But if I give you, let's say, 1 mole of Na3 and 1 mole of S plus, you don't know what could be the amount of electron moving from Na3 to the S plus, because now at the product NS4 plus, the pair of electron is shared between hydrogen and nitrogen. It's not like 2 electrons fully moving to the S plus. So because they share the pair of electron, so the density, the electron can be found in the hydrogen, but also in the nitrogen. So you cannot say in 1 mole of NH4 produced from 1 mole of NH3 and 1 mole of S plus, how many electrons? What could be the number of mole of electron is transferred from NH3 to S plus? So we say there's delocalization of electron, but we cannot do the measurement to define the amount of electron effectively transferred from the base to the acid. However, for the oxidation reduction reaction, if you take zinc plus copper 2 plus, you make zinc 2 plus plus copper. So now you know that if you have 1 mole of zinc react, it will generate 2 electrons here, and then it will calculate 2 mole of electron will transfer from zinc to the copper. It says that if you take 1 electrode of zinc and another electrode like copper, carbon, and you immerse in the solution of copper 2 plus, then it will make the wire. You can do the measurement to know 2 mole of electron transfer through the surface to be here to make the reaction of copper 2 plus become copper. So the difference between acid-base and redox reaction is in the fact that we talk about the delocalization and electron transfer from the base to the acid, and from the reduction to oxidation, from the reducing to the oxidizing component. But in the case of acid-base, you cannot do any measurement to quantify the amount of electron transfer. However, in the case of redox reaction, you are able to do this kind of calculation, you do this kind of measurement experimentally. That means it's not only the imagination that electron is delocalized, but now you can observe the electron transfer from the reducing agent to the oxidizing agent. Okay, is it clear?
Yes.
Okay. So now we talk about the precipitation reaction. Precipitation reaction, what is the reaction when aqueous solution or ionic compound are react each other and a solid precipitate is produced, is formed. So let's say if you pick up magnesium chloride and you put in the silver nitrate, you put with the silver nitrate in the solution, you will have silver chloride precipitate and the magnesium nitrate dissolve in the water. So for example, here you can see the phenomena. You take the magnesium chloride solution and then you put the silver nitrate solution inside. You can see quickly the white powder appear. So now, in solute, you have a solute and insolute. So what could be the level of solubility to say that one compound is insoluble in water or insoluble in the solvent? So one compound is quantified as insoluble if this substance have a solubility of less than 10 millimolar per liter, millimole per liter. So to predict whether a precipitate is formed, we note the ion present in the reactant. We consider the possible combination of the cation and anion, and you use the solubility table to determine if any of the combination is insoluble. Okay, so let's say if you need to consider the case of magnesium nitrate and sodium hydroxide, so first you note the presence of the reactant. So here you will have this one, you will have magnesium 2 plus, nitrate minus, and you will have a sodium positive and OS minus. Okay, so that's first step. The second step, consider the possible combination of the cation and anion. So if you take the magnesium, you can combine with the magnesium nitrate. So the reactant, the compound you use for the reaction. So basically, it's in a solution. That means it's a high solubility. You can have a second possibility to combine with OH2 minus, OH minus. So in this case, you will produce magnesium OH2. Huh? The same for the sodium. The sodium can combine with OH and also combine with Redox. If we combine with the OH, so you have the reactant. So you can expect to combination with the nitrate. So you have NaNO3. So now you need to use the solubility table to determine if any of the combination is insoluble. So we need to define whether this one is insoluble or this one is insoluble. Okay, so basically, when you take this table, you will see that this compound is insoluble. So you have this precipitate. So here you have the solubility rules. Let's say for the hydroxide, we say that most hydroxide are insoluble, except the group 1A calcium hydroxide, barium hydroxide. So in previous equation, we have magnesium hydroxide. So it's insoluble. So you have the magnesium oxide at the precipitate. So I explained already. So now, imagine that you have not sodium chloride, but if you have the solution, the mixing solution of less nitrate and sodium iodide, not chloride, iodide. You will see that by doing the same thing here, you have lead 2 plus, nitrate, sodium iodide. So you have this Campbell precipitate. So let's say when you have the less nitrate, it's fully soluble. You have sodium iodide, is fully soluble. So you put inside, you have the less iodide, which is yellow powder precipitate. So you observe this one. This experiment in high school, you call what? You call raining gold, right? Because when you put it, when you put the solution of sodium iodide inside the lead nitrate, you will quickly see that the yellow powder start to precipitate like raining. So they call the raining gold experiment. It's quite nice. So this is funny experiment, nice to observe, but not very useful for the technology. However, if you take this Campbell, this one, and then you do the mixing with the ammonium, methyl ammonium iodide, then you have this Campbell, which is a new family we call the perovskite. So here is the structure of perovskite. So here you have iodide, and here you have lead, and here you have ammonium, the big one. So what you can see, this Campbell is a semiconductor, and it is very efficient to make the solar cell. And what is amazing is that the people working on renewable energy start to use perovskite for making solar cell in 2009. And quickly, just 6 years later, they can achieve 20% of solar to energy conversion. Only, you see, only 6 years later. To reach this evolution for the thin film technology, you would need 30 years. For the organic solar cell, that's a famous scientist working in organic solar cell, Professor Nguyễn Thục Quyên at Santa Barbara University, a famous scientist, Vietnamese scientist. They need about 20 years, you see. But for perovskite, it's okay. We call the emerging solar cell material because in a very short period of 6 years, they reach the record, the world records in the solar to energy conversion. However, there's one big problem. This Campbell perovskite is extremely sensitive to water. So if you make the reaction with water, you will have O2 quickly and C8-3NS3I, like this one, in the water. Then the Campbell is not stable. So that's why even the solar cell have a very high efficiency, but people working in the silicon solar cell say that there are no future for perovskite solar cell because this Campbell is very sensitive to the humidity, to the water. So as soon as it see the water vapor, it will quickly decompose. So now one of the challenging technological challenge for the people working in the renewable energy is identification of the methodology to stabilize perovskite, to avoid the interaction of the perovskite with water or make the interaction with water is less violent. That means you can accept the interaction with water, but then the decomposition is slow. Or you can make some protection to fully suppress the interaction of perovskite with water. That's something, a huge challenge, I have to say, because when especially in Vietnam, when you put any device outside in the outdoor, you have the humidity of 80%, right? Huge amount of water vapor in the air. So how we can protect perovskite for the atmosphere, like in Vietnam with a very wet environment? is very challenging, but who knows? Hope that some of you can be interested by this question, and why not a bright future for the renewable energy in Vietnam. Okay, so when you put the molecular compound in the solution for making the reaction. So first we look at the molecular equation. We saw the complete chemical formula of the reactant and the product. So we see here, sodium sulfate react with barium hydroxide. So the product will be sodium hydroxide and barium sulfate. It's something you learned at the high school already. Then we complete the ionic equation. We saw all the strong electrolyte and ion, and all the other substance, non-electrolyte or weak electrolyte or gas, by their chemical form. So in this case, sodium sulfate is a strong electrolyte. So you have a sodium cation, sulfate anion. We have a barium hydroxide. We make like into barium 2+ and OH minus. In the product, NaOH, then it's also a strong electrolyte. It will completely dissolve and solvated to make sodium and OH minus. Only the case of barium sulfate, which have low solubility, we call insoluble. So we keep the full formula, because anyway, the solvatation of this compound in water will be very weak. In other words, the dissolution equilibrium have very small equilibrium constant. So we, for the moment, we say that is fully precipitate. So then we saw only the reacting species in the chemical reaction, because the sodium ion you see in the reactant, you see it remain in the solution after the reaction. So we say that it's not active ion, but a spectator. That means something who observe, which observe and not fully involved in the reaction. OH2 minus as well is stand in the reaction after the reaction completes in the solution. So it means that it's not really involved in the reaction. It is a spectator, but not reactor or reactant. So we remove all of this spectator. We have the final reaction, which contain only the reacting species really involved in the reaction, making barium sulfate precipitate. So we have the lead ionic equation, contain only barium sulfate and making the barium sulfate precipitation. Okay. So here, a step in to write a lead ionic equation. First, you write the balanced molecular equation. You need to predict the product by exchanging cation and anion in the reactant. The second step, you separate strong electrolyte into ion. Use the solubility rule to predict the insoluble product. When you have a gas compound, it will be not soluble in the solution. And then you cancel the spectator ion, like sodium and the hydroxide ion that I mentioned in the previous slide. And then you use the remaining species, which are reacting species, to write the lead ionic equation. So in that previous case, which is barium and sulfate. So let's consider the case when you put in aqueous solution silver nitrate and sodium sulfate. Write the lead ionic equation, net ionic reaction. So first, you put in the step 1, you put silver nitrate, sodium sulfate as a molecular formula, and then it will generate nitrate, sodium nitrate, because it's exchange between the sodium and silver cation. So the product will be sodium nitrate. And when you exchange the sodium with the silver, you will have the product silver sulfate. So now important, you need to look at the second step, which one is insoluble. Because we know that because of solubility rule, when we look at the solubility table, all nitrates compounds are soluble. but the silver surface is insoluble. So we keep this. Now we split the equation into the strong, using the strong electrolytes and divide into the cation and anion, and the silver surface, because it's insoluble, we keep in the formula, molecular formula form. Then we cancel the spectator. So here the spectator are nitrates, sodium. So finally, you write the net ionic reaction. Silver surface become silver surface precipitate. Okay, so it's quite simple. Now, we talk about the acid-base reaction. Here is something important, not very difficult to understand, but in terms of philosophy is something important to see. It's quite nice example to explain to you how the theory in chemistry and the theory in the science general is evaluated, developed over time. Looking at the definition of acid and base. So the first definition of acid base is proposed by Arrhenius. Arrhenius proposed that acids, later we call the Arrhenius acids, is the compound that can produce H plus in the solution. And a base, later we call Arrhenius base, is the compound that can produce OS minus in solution. Because at the time when Arrhenius proposed the acid base definition, they know about the compound like H4, H3BO4. So definitively this compound, when you put in the water, in the solution, it will generate H plus. So this the compound we call acid, or even formic acid if you want. When you put in water or in solvent, it can generate H plus HCO minus. So we see it generates H plus. So we call Arrhenius acid. And then for the base, it can produce OH minus, like NaOH. You see Na plus OH minus. It's very nice. Definition is perfect. But then later, they recognize that the compound like Na3 behave quite similarly to other compounds defined like Arrhenius base, like sodium hydroxide, barium hydroxide, calcium hydroxide. So ammonia can be quantified in terms of chemical property, in chemical behavior, like a base. However, Na3 cannot produce OS minus in solution. So we get stuck with the Arrhenius definition for a base. So they propose us, okay, when you put this one in water, it will reach this equilibrium, and it's 4 plus OS minus. So you still produce OS minus. So it seems that Na3 can fit for the definition made by Arrhenius. Okay, fine. But then later people say that not only ammonia, but other amide like Na2 behaves also at some level similarly like ammonia, Na3. But this compound, when you put in water, you cannot produce any OS minus. So we got stuck with some exception. They are still base, but they do not follow the definition made by Arrhenius. So you say that now the definition, the theory made by Arrhenius need to be developed, need to be extended. So the Bronsted, another scientist, Bronsted, propose a new definition of acid base. They say that Bronsted acid, the acid is a proton donor. As a proton donor and produce H plus solution is quite similar. The difference is that at a proton donor, you can expect to have all the even ROS. The ROS cannot produce S plus in the solution, but it can give the proton. You have OH minus plus S plus. Depend on the chemical reaction, depend on the solvent. So now ROS can be defined and also as the Kronstadt acid. And the Kronstadt base, the base now is not produce OH minus, but it can accept the proton. So it's nice because these amine, if you make the reaction with the proton, you can have RNA3 plus. That means this compound can accept the proton. So you see that now the definition of Kronstadt cover all the exam defined by the RNAs, but also expand the definition to some compound which are not covered by the RNAs definition, but still acid base. If you take the concept in the math, if you take the concept of a compact, let's say, they are the RNAs. Acid base. So all the acid produce S plus, all the base produce S minus, and then you have some exception. For example, RNA2, which is still a base, but not in the definition of RNAs. So they cover this definition by process. This is base. Now RNA3, RNA2 become a base because it can accept proton. Of course, all the base in RNAs like NaOS still the process base because it can accept proton as well. So let's say NaOS plus H plus become Na plus H2O. So this one also a process base. Now it's perfect, right? Then you have some compound like iron 3 plus. It behaves like acid, but it will not be able to give the proton. So it's not a proton donor, but it's behave like acid. Let's say when you put in the paper with some color indicator, the color indicator change. So it's behave like acid. Then people need to develop the theory by extending the concept of acid base by using the Lewis acid base concept. Lewis acid is compound that can, instead of proton donor, it should be electron acceptor. So the Lewis acid could be able to accept electrons. When you accept electron and you can give proton, is quite similar. But then you can extend the concept to the iron, like iron 3 plus can now become a Lewis acid. So you see, the Lewis acid base definition cover all the process acid base. And then Kronstadt acid base cover all the RNA acid base. So the message is that you develop the theory to cover the new experimentation you observe while satisfying all the experimentation the previous theory already cover. So you extend the compact. Okay, so that's the main message I would like to share with you. So now you can understand very well the difference between the aryanic acids, Kronstadt acids, Lewis acids, okay? So this slide quite classic. You have strong acids and then there are anion. So you have HCl anion will be Cl minus, something quite easy. We don't need to talk more about this. You have a weak acid and the anion, so it's quite easy. You have a strong base. You have some insoluble base and weak base. For example, insoluble base like copper hydroxide, zinc hydroxide, iron hydroxide. You have some weak base, Na3, or any related nitrogen containing compound. For example, the amide, or for example, this compound also, the pyrrole compound. So you have here non-bonding electron pair, so it's behave like a Lewis base. It's a weak base. Okay. Oof. Sorry. Okay. Here, this one is a table showing the electrolytic behavior of common soluble ionic and molecular compound. So when you have an ionic compound, its own become a strong electrolyte. You will not have any ionic compound which is weak electrolyte or non-electrolyte. If you have a molecular compound, that means inside you have own the molecular equivalent bond. You can have a strong electrolyte, for example, strong acids, H2SO4, for example. You can have a weak electrolyte, for example, weak acids or weak base. Or you can have a molecular compound which is non-electrolyte, for example, fructose I mentioned, or some ethanol, methanol, and so on. So really depending on the equilibrium constant, that we can decide whether it's strong electrolyte, weak electrolyte, or non-electrolyte for the molecular compound. For the ionic compound, all will have a very high value of the equilibrium constant.
Professor, what about the strong base?
What do you mean?
What about
what's the question?
I'm asking, what about the strong base, or why can we classify it into the cell?
The strong base, right? The strong
Yes.
base will be the ionic compound here. So all is strong electrolyte.
Oh, okay.
Okay.
Okay, thank you.
Basically, a strong base is ionic compound. So for all the ionic compound, because the equilibrium constant is very high, the solventation is very high, so you will have a strong electrolyte behavior. Okay. Of course, for those who can be soluble, if they are precipitate with low solubility, then we cannot consider, right? Because with electrolytic behavior, we talk about the soluble compound, right? If you have, for example, silver chloride, we cannot qualify as a strong electrolyte or weak electrolyte because it's not soluble. Okay.
Okay, thank you.
So for the neutralization reaction, that's the reaction between acid and base. So you produce sauce and water. So it's something you learn in high school already, not a big problem. So here is the phenomena. You have a milk of magnesium. So that means the magnesium hydroxide in water. So you see that it's not soluble. It's insoluble, the magnesium hydroxide. So when you put in water, it's make a dispersion, not a solution. And then you take a solution of hydrochloric acid, HCl, the white solution here. So you see that magnesium hydroxide start to dissolve when you add the hydrochloric acid inside. So the dissolution of the magnesium hydroxide indicate that magnesium hydroxide is disappear or consumed in the process of the chemical reaction happen. And then at the end of the reaction, you see that the clear solution contain only soluble magnesium chloride. So we can write the chemical reaction. You start first from the molecular equation, and then you suppress on the spectator ion. That means the spectator ion mean the ion who not really involved in the reaction. So then you, in this case, is chloride. So then you you achieve the net ionic equation involve those who really involved in the dissolution of magnesium hydroxide, which is the proton and magnesium hydroxide. Okay. Acid-base reaction with gas formation. So many base beside OS react with H+ to form the molecular compound. For example, when you have HCl, you put in sodium sulfate, you have H2S gas produced. Be careful, it's extremely toxic. It smells very strong and toxic. So basically, when you come back to the when you come to campus, USTH, my research lab located at the 7th floor. So basically, you are in the first year. So you mainly have a lecture in the 8th floor, in the main lecture room, in the 8th floor. And if you have time, you can visit my research lab at the 7th floor. And if you visit our lab, very likely that you have a chance to smell H2S. You smell some thione compound because my research lab working a lot with the sulfur compound. So when we do the acidification, we do the synthesis of the sulfur compound, we can generate thione, or in some instance, we can produce amount of H2S. So it smells terribly. Sometimes we do experiment in 7th floor, and the office, on the office in 1st floor and 2nd floor can smell. You have another compound reaction, like you do the acidification of the carbonate solution. So you have the product CO2 produced, is acetic gas. Now, we move to the oxidation reduction reaction. We call the redox reaction. Redox, that means a reduction oxidation reaction. So as we mentioned, the reaction involves a transfer of electron from one species to another. So here, showing you the experiment. When you take an iron, you put in the copper sulfate, and what you see that the iron start to change the color on the surface, and at the end you see the copper brown color appear on the silver, on the iron. Sorry. So the reaction is a redox reaction. You have irons, it's oxidized, which reduce copper 2+ to make iron 2+ and copper metal. So the copper metal will stand here. What is it? Sorry. Don't know why. Okay. So you see that here, the copper stand on the irons. So the reaction, the net ionic, first you put the molecular equation, and then you have, you suppress on the spectator ion, which is, in this case, is the sulfate. So you have a net ionic equation with the iron plus copper 2+ become iron 2+ and copper 0. So the copper with 0 will stand on the iron surface. Okay. So we talk about the oscillation number. Oscillation number is hypothetical charge assigned to the atom, assuming that the electrons are completely held by one atom or the other. So it's a way to keep track the electron transfer. Okay. Here you have some rule for assigning the oscillation number. All the elements uncombined have oxidation number 0. So we have aluminum, metal, nitrogen, silver, oxygen, all are 0 oxidation number. If we have a monoatomic ion, so the oxidation number equal to the ion charge. So you have potassium plus, so that means the potassium have here oxidation number +1. Add 2 minus, that means the oxidation number is -2. For non-metal, usually have a negative oxidation number. So oxidation have a 2 minus and fluoride 1 minus. 1 minus is representing the capability to attract electron, because the non-metal number, will have higher electronegativity compared with the metal. So the tendency is that the metal will give electrons, so it's become positive charge, and the non-metal will receive electrons to become negative charge. So to representing this tendency to receive electron is have a negative oxidation number. So the total of the oxidation number should equal to the overall charge. For example, if you have H3O plus, the total oxidation number inside this species should be +1, equal to the charge. So that's the case, because proton, you have the oxidation number +1, and oxygen, you have an oxidation number -2. So that means H3, you have a +3, -10, -2, that means you have +1, overall equal to 1. It's quite easy to do this calculation. So if you want to assign the oxidation number for all elements in this species, so basically here we can see that oxygen will have -2. So -2 is equal to -4. So that means the sulfur should be 4 plus. So +4 if you want. Sorry. +4. Okay. For the bromides, it's -1. So the magnesium should be +2. Oxygen here is -2. So in total, you have a -4. And the charge is -1. So that means the chloride should be +3 here. It's quite easy, this kind of assignment. So you can do some exercise in tutorial class to make it. So oxidation, now we have concept of redox reaction. Now what could be the oxidation process? Oxidation process happen when a substance lose electron, the substance is oxidized. Okay. In the inverse, reduction is process happen when a substance gain electrons, that means receive electron. So in this case, the substance is reduced. So to balance electron, because one compound oxidize, that means it give electron, should need another compound receive electron. So that means one compound should be reduced. That means the oxidation and reduction should be happen simultaneously. Sorry. Otherwise, you will have excess electron, and it should be not happen. You can drive the electron in the external circuit, but at the end, the electron should be balanced. So you have iron oxidized by 2 electrons to become 2 plus. Then you remove 2 electrons. That means you should have other reducing agent. That means other species to be reduced by receiving the 2 electrons. So for example, here in the case, you have iron oxidized 2 electrons. Then you have a copper reduced by 2 electrons. So that means electron lost by ions and gained by the copper. So oxidizing and reducing agent. Oxidizing agent, that means the compound oxidize other substance. Reducing agent is compound that reduce other substance. So in this case, irons give electron to reduce copper. So iron become reducing agent. And copper receive electron from the irons. So that means it's oxidize irons. So copper 2 plus is oxidizing agent. Okay. So if you have one element replace another element in a compound, So then we have a displacement reaction. That means one element takes the place of another element in a compound to produce a new chemical component. So we can say that active metal replace or displace a metal ion from a solution. So if you have a magnesium, you put in a copper chloride, then the magnesium will take the position of copper, replace the copper to produce magnesium chloride. So in that case, copper will be released from the copper chloride. To predict this displacement reaction, we take a look at the activity theory of metal. So here is activity theory. So when you go from the bottom to up, the oxidation, the possibility to be oxidized increase. That means all the atom in the bottom, on the metal in the top, on the metal in the top will be easily oxidized, and the ion in the bottom will be easily reduced. Okay. So let's say the copper can reduce silver to make copper 2 plus and silver particle. So let's say here you have a copper wire, you immerse in the solution of silver nitrate. You will see on the surface that here the silver particle, silver start to grow on the surface of copper. So at the end, you will have the copper wire covered by the silver. Now, imagine here I have a copper wire, okay? Inside, I have silver, like this. Here, I have silver, okay? So first, the reaction happened. So I have silver here. Now, what could be the next reaction? Whether the silver will develop like this one. That means this reaction actually happened on the silver. Or I will say that that's the possibility A. Yeah? The possibility B is that the copper, first silver will happen here, and then continue happen here, 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 here. And then at the end, I will have one layer of silver fully cover the copper, and then the reaction stop. That means if you keep in the case of B, if you keep the copper inside the solution for a long time, the reaction will stop because the surface of the copper will be protected by the silver layer. If this is the case of A, that means even you keep for a very long time the copper in the solution, the copper will fully dissolve, the redox reaction will never stop. The copper will continue dissolve, and you have the final fully silver, and all the copper become copper 2 plus, and this will be fully dissolved. Do you understand my explanation?
Yes. Yes.
So now my question is, in your opinion, what could be the situation whether if you keep for a long time, the process will be the process A, that means the copper continue dissolve, and you produce all the silver, and then the copper wire will be fully dissolved, or you will have the case of B, the reaction will stop somewhere after some time because you have one layer of copper, one layer of silver fully protect the surface of the copper, and then copper cannot be dissolved anymore. Where the process would be.
Logically, it could be B.
Yeah, it should be B.
Normally, but who knows?
B?
Yes.
Normally.
Normally,
I mean,
it should be
if I
B.
put copper, okay. So to answer whether A or B, the in our lab, when we put the copper wire, copper video, how the silver, and from this video observation, and whether it will be A or B in this reaction. Okay. Hold on a moment. I'm trying to see how I can share the video. I propose that we back to our lecture.
Okay.
Hello. Okay. So basically, I try to take photo at different instant when the video play. So on this picture, you can see that here you have silver. Okay. So basically, the copper wire is somewhere here. So you see the silver here. Okay. So that's the moment when we start the video. Can you see that?
Yes, we can.
Okay. Then I move to the second video. You see the silver wire before is stick here, right? And then it's developed by this way. You see it's developed like this one. Silver. And then if I change to the last photo, when you have final, you see? So basically, the silver start from here, and then it develop like this one, this, develop like this one. So we call this one is silver dendrites, or in general we call the metal dendrite. Okay, so can you see the image?
Yes, we can.
Okay, so if we back with this observation, so sorry that I cannot show you the video, which is very nice. We try to record it. So basically, based on the image we see, it's like you have copper here. First, you make silver, and then silver develop like this one. Huh? So it's actually like you have a copper here, copper, remove 2 electron, become copper 2 plus. And then the electron will go, you can imagine that the electron flow on this copper, on this silver, and where in the solution you have silver plus, right? So the silver plus will be reduced to make silver. Huh? So that's why the process developed like this one. Do you understand what I mean? So if you keep the reaction happen, if keep this reaction for a long time, all the copper white will be dissolved, and you have a silver in this kind of dendrite. Okay.
Okay.
So basically, this copper reaction with the silver ion to make the silver dendrite is a phenomenon which is, if you look at the video, it's very nice, good to see. But it's also very important in the current technology, because let's say when in the lithium battery, last week in the new paper, in new journal, people talk about the VinFast company. They decide to stop on the production of the gasoline car, and then move to the chick car, right? So when they want to run the lithium to have a lithium battery, so I remember that I shared with you the configuration of lithium battery. So basically, you have one lithium anode, right? So that's a perfectly redox reaction, and you have cobalt oxide cathode. Huh? So when the battery, and in between, you have a membrane that should be porous. So what will happen when it's work? So the lithium in anode will make the reaction lithium become lithium plus, and then you have an electron, right? The electron will go to the cathode, and when you go to the cathode from the anode, that means you have electricity. Then the lithium will go here to make the reaction. So the lithium plus COO2 become lithium COO2. Okay. Then that's when the battery operates. That's when we call the discharge. So at the end, when the battery is already empty, you need to recharge it. So when you recharge, you do the invert process. That means the lithium here, lithium from the lithium oxide, cobalt oxide, become lithium iron, and it will be back to the anode, where the electron will flow back, and the reaction make the lithium. So here, the process will happen on the anode. If the reaction, you have the anode here, if the reaction make one layer of lithium anode, due to this reduction, lithium plus one electron become lithium, then you will have a perfect lithium anode will be reconstructed compared with the starting state. However, if the reaction between the lithium plus one electron happen by the same manner like silver here is work like this. So it means the lithium will deposit, become lithium metal, but instead of making one layer like this, it will develop and making lithium dendrite. What will happen? It makes that at some moment, this lithium dendrite can be go through the membrane and then reach the lithium dendrite will contact directly with the cathode. In that case, you will have a cathode anode in the contact, electric contact, so the battery will have a short circuit. That means it will not have any battery anymore. So the battery will be die. So if the car want to be used for a long time, let's say you are not ready to change your battery in the VinFast car every year, right? Every month is not possible. VinFast, Golden Task, they will change the battery for you after 3 years of using battery. That means the lifetime of battery should be more than 3 years. So to reach more than 3 years, one of the phenomena you need to suppress is the making of lithium dendrite. So you need to suppress this dendrite process and make only one layer of lithium on the anode like this. And you see, when you put the copper wire in a silver, you see the dendrite happen naturally. So that means the reduction of lithium metal to making the lithium dendrite is something natural. It could happen. So to stop something which is naturally is challenging. And one of the challenge for development long time using long life lithium battery is stopping this dendrite growing process. So you see that something is very funny in the chemistry, general chemistry, but actually it represents a huge technological challenge that RD scientists or technology is trying to deal now in the industry. You understand the point here?
Yes.
Understood.
So that's why I asked my PhD student try to record the video when the silver dendrite growing to have a clear vision on the growing. Normally during the class at the university, I can share with you this video, but online I don't know how to do for the moment. So sorry for that. So now if you are asked you are given two compound iron chloride and magnesium, when they react with each other, to answer question, you need to look at the chemical activity theory. So let's say you have here, you have a magnesium here in the activity theory, you have a magnesium here, and you have an iron compound here, okay? So basically, the magnesium have higher activity to be oxidized than the iron. So the tendency of reaction will be magnesium plus iron 2 plus, giving magnesium 2 plus iron. Because the magnesium here have higher activity to be oxidized, so it can be easily to oxidize to the magnesium 2 plus, and the iron 2 plus can be easy to be reduced to iron. Okay, so the reaction will happen. But if you put magnesium 2 plus iron, then it's not happen, because the magnesium, the iron have lower of activity to be oxidized. That means the process to become iron 2 plus is more difficult than the magnesium. Okay, so in this reaction, the second one, there no reaction happen. So later in the second semester, when you learn general chemistry 2, this process will have standard potential. Okay, and this process, iron, you have also a standard potential. We call the potential of magnesium 2 plus magnesium. And here you have a potential iron 2 plus iron 0. So to examine whether the reaction happen, what you have to do, is you calculate the delta E. Huh? So it's by the K dot, that means the E of iron 2 plus iron minus the E of magnesium 2 plus magnesium. So if the delta E larger than 0, that means the delta G equal to minus NF delta E. Smaller than 0, that means the process is downhill. If the process downhill, that means in terms of potential reaction, and then the product like this, the process is like this, that we call the downhill. So the process will happen. That means in the general chemistry 2, you will not learn to calculate the delta E, and from that you calculate the delta G. And when the delta G is smaller than 0, the process is happen thermodynamic point of view. But after that, whether it's happened fast in the high rate of reaction or low rate of reaction, we talk about the kinetic is other space aspect. Okay. But for the moment, before learning about the calculation of delta E and delta G, free give energy, you accept to remember this activity theory to predict whether the one reaction happened or not. So we can go to have other classification of chemical reaction. So we talk about the 4 categories. We talk about the first one, synthesis or combination. That means you have two components combined together to make a product. You talk about decomposition. That is invert of the combination. That means you take one compound, decompose into two components. You talk about displacement. So the compound A or element A will take the plus of B to make the product AC and release the B. We talk about the double displacement. So A take the position of C and C take the position of A. So that is the exchange reaction if you want. Here we take some symbol exam, some symbol demonstration of the 4 class of chemical reaction. So we talk about the combination reaction. So you see sodium plus chloride, sodium chloride, calcium oxide react with CO2, they become calcium carbonate. The decomposition reaction is inverse. So one of the challenging one, basically this one. So my research lab work on this chemical reaction. That means splitting decomposition of water into hydrogen and oxygen since now about 10 years. So we need to work on different catalysts to accelerate this decomposition reaction. It's not easy at all, very challenging, but interesting for the future. So we talk about the displacement. So you have a zinc, copper chloride. So that is the classical galvanic reaction. So we talk about the Volta battery, Danyan battery, if you want. You talk about the double displacement, for example, silver nitrate plus sodium chloride and so on. Of course, sometimes you have reaction what could be challenging to put exactly in one of the 4 categories. So one chemical reaction we call the displacement actually. So you know that's when the submarine, when the soldier working in submarine, they breathe, they will release CO2. And because the submarine work under the water, so they will need to have, of course, the soldier survive, need to have oxygen. So they breathe in oxygen and release CO2. So now the technical question is how we can remove CO2 and then generate oxygen to support the living of the soldier inside the submarine. So basically you have 2 systems. You need to absorb, you need to remove CO2. And then you need one system to generate oxygen. Then the chemists have a brilliant idea to combine both the two processes in one single chemical reaction. Anyone know what kind of chemical reaction they use to absorb CO2 and produce oxygen in the submarine? Any one of you know about that? Anyone? Do you know about that?
No.
No?
But I could guess that they might use a reaction that is similar to those that happen in the plants, maybe.
But you know that the reaction in the plant have the efficiency of only 1 to 4%. The production here is only 1 to 4%, you know, so it's quite not very efficient because the plant have a time to do the reaction. But in the submarine, you know, that's you need to release oxygen quite fast and absorb. That means remove of CO2 very fast as well, right? Otherwise, the atmosphere inside the submarine can be not become unsupportable for the solder. So basically, they use a chemical component, which is this one. Okay, so this one is quite similar to H2O2. It's like oxygen minus, and you have sodium. Okay, and what will happen if you put CO2? It will become NaCO3 plus O2. So you see that one molecule CO2 absorbed, it will release half molecule of oxygen. So this is also a displacement reaction, right? So interesting is that at the same time, you can remove CO2 from the atmosphere and then generate oxygen into the atmosphere to keep the environment inside the submarine supportable for the living of the soldier. Okay, and the sodium peroxide is a solid compound, so it can be easily to be stored and transported during the military mission. So if we talk about the combustion reaction, that is the reaction you make with oxygen. Actually, it's normally a rapid reaction and release a huge amount of heat, and because all of the combustion reaction are basically they are exothermic. So it will produce one or more oxide. And then in this combustion reaction, the oxygen change the oxidation number from 0 to -2, basically, it's -2. Okay, and remember that last time we discussed about the single spin or a pair electron. Oxygen in the normal state is triplet. That means you have 2 single electrons. So all the other compounds have no single electron. That means all electrons are paired. They cannot react with oxygen in the normal condition, in the ambient condition. That explains why the natural gas, for example, CH4, you can open CH4 cylinder in the oxygen without any explosion, without any reaction. But if you have excitation, then you change the oxygen from the triplet to singlet. That means 2 electrons singular become pair electron. Then it's going to react with the methane. Or if you excite methane from the singlet to triplet, it also reacts with oxygen. So the key of the combustion reaction and also other combustion reaction is that the singlet will react with singlet and triplet will react with triplet. So that's explained when you want to understand the chemical reaction, understanding the electronic configuration of the compound are extremely important. Now, we move to something very simple that I'm sure that you are very strong, because you learn a lot, you calculate a lot, you practice a lot for the preparing of national exam, graduation exam. So we talk about the working with solution, we talk about the molar concentration, and we discuss on how diluting a solution. So recall solution is homogeneous mixture of the solute and the solvent. Solute have a smaller content being dissolved in the solvent, which have a higher quantity in the solution. The solute mean when dissolve. So we talk about concentration. Is the quantity of the solute in a given volume of the solution, which is usually 1 liter. So you have the concentration is the mass of solute over the volume of the solution. Let's say 10 gram per liter or 20 gram per liter. That when you check Wikipedia, you search about the solubility of 1 compound, they will give you the concentration of saturation concentration. That means the maximum solubility is 20 gram per liter. So that's the quantity of the solute in a given amount volume of the solution, which is usually 1 liter. Then we have the molarity. That means the molar concentration, the number of mole of a solute that are present in 1 liter. That's easy. You take them to make the molarity, you take the number of mole of solute over the volume of solution. So between the molarity and the concentration, the difference is you need to take care of the molar mass, so molecular mass. If you take the molarity multiplication with the molar mass, you have a concentration, and if you take the concentration, you divide by the molar mass, you have molarity. It's quite easy. So you calculate the number of moles. Now, the question is following. When you do an analysis, let's say your professor say, do the measurement of the conductivity in function of sodium chloride concentration or the molarity. So what do you expect? You need to prepare a function. Here you have conductivity, and here you have concentration or the molarity. So to do that, you need to prepare a series of sodium chloride solution with different molarity. For example, you need to prepare one solution with the 10 millimolar, one solution with 100 millimolar, one solution with 5 millimolar, one solution, let's say 50 millimolar, and one solution with 1 millimolar. Okay. So now, how can you do? You have one possibility. Let's say you prepare, because X experiment, you need to prepare 10 milliliter for one experiment. So first you prepare 10 milliliter of 100 millimolar. To do so, you calculate the amount of sodium chloride in terms of mole, and then you calculate the mass of sodium chloride that you need, and then you weight. You do the weighting of this mass, you disperse in 10 milliliter of the water, so you have this solution. You do the same thing with 10 milliliter of 50 millimolar. You calculate the number of mole of sodium chloride. You calculate the mass of sodium chloride that you need to take from the bottle, and then you do the same thing. So that means you need to do the weighting for several times. 1, 2, 3, 4, 5. You need to do the weighting of to obtain the mass of sodium chloride for 5 times. And each time of weighting like this, you will make one error. So basically, the solution you prepare, 100 millimolar, that can be not exactly 100 millimolar, but that can be 100 millimolar plus or minus 2 millimolar. That can be 98 millimolar. It can be 102 millimolar. And then you do the second weighting for making 50 millimolar. You can reach an error. You make 50 plus 4 millimolar. That means another kind of error that you cannot control because another weighting. So by doing so, you will have this kind of, instead of having a linear evolution like this, you will have this kind of data experiment. And then when you make the fitting like this, you make the relationship between the conductivity and the solution, the molarity, you will have a strength evolution. Because when you do the weighting here, preparation of solution here, you make already several errors in the experimental error. That is not a systematic error, but that is a personal error. So in the analytical chemistry, to minimize this kind of personal errors, you try to minimize the number of weighting. That means you do only one time of weighting, but prepare for all the solution you want. So how can you do? First, you will prepare the 100 millimolar solution. So you do the weighting only one time. Then now you have 100 millimolar. If you want to prepare the second solution with 50 millimolar, what you can do, you take 5 milliliters of this solution, you put 5 more milliliters of water. So you will have 10 milliliters of solution with 50 millimolar. So by doing so, you will have limit error. You will not need to weighting anymore. And then to prepare the 10 millimolar, you take the 100 one, and then you take 1 milliliter, you add 9 more milliliters of water, so you will have a 10 milliliter of solvent of solution with the concentration of 1/10 times 100. That means 10 millimolar. And then when you have a 10 millimolar already, you divide by 2. That means you take 5 milliliters, you plus 5, you add more 5 milliliters of water, so you will have a 5 millimolar. And then when you have 5 millimolar, you want 1 millimolar, or you have 10 millimolar, you want 1 millimolar, you dilute by 10 times. So instead of multiply several times of the weighting with solid, which make a different error, what you can do, you prepare one concentrated solution with higher concentration, higher molarity, and then you take this like a stock solution, and then dilute it at 1 to reach more diluted solution. So we call the preparation of a solution by dilution method. That is the method usually in analytical chemistry you will apply. Okay? Any question? No?
No
Thank
question.
you. So this kind of exercise you can do at home. We do not need to solve here. Solution stoichiometry, no problem. This one easy to understand. So we move to the last question. Quantitative analysis. So quantitative analysis is try to determine, or the process of determination of the amount of a substance or species present in a material. So let's say you are given a solution. You need to define the concentration of, let's say, silver in one solution, or determine the concentration of arsen in water in Hanoi, for example. So to determine the amount of this arsen in water, we need to process the quantitative analysis. So in the practical chemistry class, in the second semester, you will practice on two methods we call the gravimetric analysis and volumetric analysis. So by the name, you can understand the gravimetric analysis, that means using the mass of the compound to calculate the amount of the species inside the solution. And using the volumetric analysis, that means you calculate the volume of the solution you use, and from that, you define the amount, the quantity of the species you need to determine in the solution. So the gravimetric analysis, you need to convert the dilute species. You need to convert the solute species into precipitation. That means you need to add a chemical compound to make the precipitation, to make the reaction with the solute species, with the solute species, and then convert it become powder, solid powder, and then you will take this powder, you make the weighting, and then you define the amount of the solute in the solution in the mother solution. For example, if you take a solution of potassium chromate, yellow solution here in the here the solution, you put in the solution which contain barium. So you will convert the solute barium 2+ into the barium chromate, which is the powder, yellow powder. So you collect the powder by the filtration, and then you dry it to remove all water, because you prepare the barium chromate in the water solution. So basically, you will have a solvated process. So around on the surface of barium sulfate, you have a lot of water. So you need to dry it to remove all the water, and then you have the exact amount in terms of mass of barium chromate. From the mass of barium chromate, you know the molecular mass. So you could be able to calculate the number of mole of barium chromate you have. So from that, you will, because the number mole of the barium in the solution should be equal to the number of mole of barium chromate, because you assume that all the barium is converted into barium chromate. So you say, to apply this gravimetric method, you should identify the compound that can convert all the solute ion into the precipitate. That means you should identify a component from the solute which have very low solubility or fully insolute. Okay. Now, about the volumetric, we can call like pH duration. That is procedure for determining the amount of substance A by adding a careful measurement volume of a solution with no concentration of B until the reaction of A and B is complete. So let's say if you want to identify the amount of HCl, chloric acid, in the solution, then you will add few drops of color indicator, which is the phenolphthalein, indicator, a color indicator. And then in the puree, you will have a solution of sodium hydroxide. So each time you add sodium hydroxide into the chloric acid, the color inside the solution, because of the color indicator present, will change. So the moment the color of indicator stable, that means you fully complete the reaction between the sodium hydroxide and hydrogen chloride. So based on the amount of sodium hydroxide you put in the solution, you know the concentration already. You can calculate the number of mole of sodium hydroxide you use. So you can deduce, you can calculate back the amount of hydrogen chloride inside the solution you need to determine. Okay, so that's all for the moment. In this class, we talk about the electrolyte. So we talk about strong, weak, and non-electrolyte. We talk about precipitation. So for the precipitation reaction, we take a carefully look at the solubility rules. That's, I'm sorry, but this the minimum thing that we need to remember. Then we talk about the molecular equation reaction. We talk about the ionic and net ionic reaction. We talk about the oxidation, reduction, acid-base reaction. We talk about the manipulation with the solution, so the concentration, molarity, and we discuss on the way, a practical way to prepare solution with different concentration to limit the personal error when making the solution. So the concept is try to prepare a higher concentrated solution and then take it like stock solution or mother solution and dilute it to get the concentration you want. Try to limit repeating the weighting of solid compound because that's it will make a huge mistake. And we talk about the quantitative analysis to determine the amount of one ion or one compound in solution that you don't know. You have two approaches. One is using the gravimetric analysis. Another, we use the volumetric analysis. So basically, you will need to use one chemical compound, fully react, the reaction completes with the species you want to determine. And based on the amount of the compound you add in, you know the concentration. So based on the mass, you know the number of mole, or you know the concentration, and you know the based on the volume you add inside, you know the number of mole react. So you assume that all the solute that you need to determine in the solution completely react with the compound, foreign compound you add inside. So based on that, you can calculate the amount of solute in the solution you need to identify. So that's all for the moment. And this will be the last lecture for this general chemistry one. Actually, I update to you the lecture material for the last class, geometry and bonding theory. So inside, you can look in the Moodle and you see that in this slide, we have some demonstration, some exam, where I want to emphasize why we need to learn about the geometry. For example, when we talk about the climate change, nowadays, last year was a big year when the climate change is emphasized again and again. And also the Nobel Prize in Physics is awarded to the scientists working on the modernization model for explaining the climate change. So physics of complex system. So, but then one important thing is that when we talk about the greenhouse effects, all people will say that CO2, halogen compound, for example, CF2, compound, when you use for the fridge at home. But then when you look at the geometry and understand what is the greenhouse effect, you understand that water is also a compound that can cause the greenhouse effect. Then I want to open the question why people focus only on comment or complain about CO2, but never talk about water vapor as an agent making also warming effect, global warming. So the exam and discussion I put at the end of my lecture on the molecular geometry and bonding theory. So I hope that you will enjoy this kind of exam, this kind of thinking, because you are student at university. So what I hope through my class is not only transfer to you guys fundamental understanding in chemical bonding, chemical reaction, and then expect that you guys survive in my midterm and final exam. What I really expect, what I really hope is that you can enjoy the discussion during my class and start to think about something, start to think about the future challenge that you guys, your generation, need to solve. And the chemical chemistry or chemical science is one aspect that can help you guys to understand the complex system and help you guys to understand the challenge and help you guys to solve together with other tools to solve the complex issue of our society. Technology like lithium, stability, climate change, renewable energy, environmental pollution, and so on and so on. So that is, and I hope that you will all work well with the tutorial class, enjoy the lecture material, and when and expect that all of you after that will have excellent performance in my final exam. The performance in the midterm exam is already excellent. In my opinion, only 90 guys should have less than 10/20. That means normally with this score, you need to retake. Only 90/600 students is quite a good score. Normally for previous generation, in the last few years, basically the rest of retake is about 50% for the midterm. But now 90/600 is excellent score to me. So keep this dynamic and try to perform well in the final exam. I'm sure that the general chemistry will be the easiest topic that you can get a high score in the first semester in USH. So do you have any question or concern about the final exam or discussion you want? Because this will be our last interaction before we close our lecture, general chemistry class. Do you have any question, concern, or comment?
Can I ask, the final exam we do it on online test, right?
Yes, will be
Okay.
the same format like midterm.
Okay.
Okay, exactly the same 40 questions for 90 minutes. I see that in the midterm, some of you only need 40-50 minutes to complete. But I still give you guys 40 questions and 90 minutes for those who want to take time to consider well, okay? In terms of question, it will cover all the topic, including the topic already checked in the midterm. That means for the final, we can review everything, okay?
Professor, can I ask when will we receive our midterm score?
Okay, so I'm going to ask my colleagues to send you the midterm score by this week, okay?
Okay, thank you.
Okay.
Okay.
And for those who need to take the midterm examination because it was absent due to the military training last time, the midterm will be conducted next Friday from 7:30. Okay. So please arrange your agenda to attend the second midterm examination. Only for those who were absent because of military training. Okay. Okay. So if no more questions, thank you all of you guys for your contribution to the class. It was not easy because online teaching is much difficult for me. You can see that I'm not very good at the technology, at IT. I'm very bad, we would say. In my laboratories, they say that Phong is anti-technology guy. I'm very bad. Actually, we can discuss more if we are in the face-to-face lecture, because we can dialogue, we can take more emphasis on the important topic. But anyway, we enjoy, at least myself, I enjoy the class with you guys. I'm very happy with the performance of the midterm. And so thank again, and may I wish you all the best for the next adventure in UATS, and hope to see you very soon in the campus face to face. Okay.
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 Bye bye.
Goodbye, Professor.
All right,
Bye,
Professor.
Professor.
Goodbye. Bye, teacher.
Professor, thank you.
Thank you, Professor.
Yeah, Professor.
Goodbye, teachers.